Hey, good morning, everyone, and welcome back. Hey, I just wanted to say good job to everybody who pushed hard to bring their grades up in the third quarter. And for those of you that may have had difficulty, I I would like to see you maybe step it up or ask for a little bit more help. But overall, I'm really proud of the work everyone has done. So, first things first, if you have not yet, I would like you to go to the attendance page and fill out the attendance form with your last name and then your first name to get counted as attendance. I appreciate it. So, as we continue our journey into learning weather, today we're going to be looking at our Pilot's Handbook of Aeronautical Knowledge, and we're going to start on page 12 12, and we're going to be getting into atmospheric stability. So, what atmospheric stability is it represents the atmosphere's ability to resist change, specifically resist change in a vertical motion. So, as the air moves horizontally over the surface of the earth, whenever you have something that applies pressure to the top of it, that essentially disrupts the entire stability of what's happening. The main factors in atmospheric stability are going to be the temperature of a select mass of air, the humidity, and the ability and pressure. So, as we know, we've talked about how air in the atmosphere actually, the density of the air reduces as you climb higher. So if you can imagine that as the air is on the surface of the earth where we live in the troposphere, it's relatively thick. There's a lot of air molecules in a select parcel of air. And as temperature is applied to it, the air will heat up and rise up in the atmosphere, where as it rises up, it's going to get thinner and thinner and cool down, and we're going to end up having a cycle that's continuous. But since you have a cycle, that means the composition of the atmosphere is going to be forever changing. So the first thing I would like to talk about is we're going to talk about something called the adiabatic process. And what the adiabatic process is that as the air rises for every so many thousands of feet, it's going to cool. So we have what's known as a standard temperature and a standard pressure on the surface of the Earth. The standard temperature, which we're going to talk about it in Celsius. The standard temperature in Celsius is 15 degrees, which is roughly 73 degrees Fahrenheit. And the standard pressure is 29.92. Anyway, so as you look at the standard temperature and standard pressure, that is at sea level. So for every 1,000 feet, it's going to drop in average temperature. For Celsius, per every 1,000 feet, the temperature will drop 2 degrees Celsius. So if I was at 15 degrees at the sea level, 1,000 feet higher, it's averagely going to be 13 degrees C. And that is the basic principle of the adiabatic process. So the next thing we're going to talk about is what's known as a temperature inversion. So as we previously discussed, that as air rises, it's going to cool. because it's not receiving direct heat and radioactive heat from the surface of the Earth. But in certain cases, you can actually be flying, and as you are climbing, the air will get warmer. It is a layer of warm air that goes over a cold air mass. So that is known as a temperature inversion. The next thing we're going to talk about is how moisture and temperature affect air. So, since we all live in Florida, I'm sure that every single one of you has encountered some sort of visible precipitation in the atmosphere, whether it be fog in the morning or a late afternoon thunderstorm, which is common through the months of May to August. So we're going to look at moisture and temperature, and what we're going to discuss is we're going to say we have a little square block of air, and in that square block of air there's going to be air molecules, and that's what we breathe. So we know that the sun heats up the surface of the earth and water is going to evaporate and turn into a gaseous form known as water vapor. Well, it's going to rise, and it's going to be present also in that atmosphere. Now, since we have our little cube of air, what we have to be able to examine is we have to look at what temperature that cube of air is, because depending on the temperature, it's going to cause those air molecules to move around, and the more the air molecules move around, it takes up space. So you would end up having water vapor and air fighting for the same space. So how does all this apply in our daily lives of Floridians? Well, if you've ever taken a shower and had to go outside, you notice that your skin can get all sticky, and that is a product of humidity. And that is because of all that water vapor that happens to be floating around in the atmosphere. So when we look at that parcel of air and we have that water vapor fighting that air, what happens is once water evaporates and it rises into the atmosphere and it becomes that vaporous form, it is actually lighter than air molecules, so you can have more molecules of water vapor fighting those air molecules to occupy the same space. And we have two types of humidity we are going to look at. We are going to look at the general definition of humidity, which is how much water vapor is present in the atmosphere in a given time. That is how much can exist on any given day. When we use the term relative humidity, that is us basically saying that we are going to measure one specific mass of air and determine based on its temperature how much water vapor can be in that one particular mass. So since we know that water vapor is present, and we know that water can evaporate, it can sublimate, and it can freeze, there's always going to be water in the atmosphere. So later, when we study aviation, weather observation, and systems, and how we can learn how to disseminate weather reports, one of the big things we're going to talk about is we're going to talk about the temperature dew point relationship. So basically, to summarize what it is that we know there is water vapor present in the atmosphere, and we know because we have that volume of air, but if we change the temperature of that air, we can get some sort of visible moisture out of the air. So we have a science of setting what's known as a dew point, and that is the temperature in which that parcel of air can hold the most moisture before you would see visible moisture in the form of fog or rain or snow or whatever. So when we know what temperature that particular mass of air has to be at for something to happen, we can create a scale. We can have a temperature dew point scale. And what that means, generally it is in Celsius, but what it means is that, say, the dew point of an area is 17 degrees Celsius, and it is 20 degrees Celsius outside, which is roughly 82 degrees. So if that temperature, which is 20 degrees Celsius, drops to 17 degrees Celsius, that parcel of air will be heated to the perfect temperature to show visible signs of moisture, whether that be, in that case, it would probably be rain. So that's all we're going to talk about for today, because I don't want to overload you and do too much, but I just want you guys all to know that I'm extremely proud of you all for pushing on. So next, what we're going to do is I'm going to ask 2 extra questions, because I just want to know that you're paying attention and you're reading your book and you're watching these videos and taking advantage of every resource to do your best. So we talked earlier about the adiabatic lapse rate. So the 2 questions I have for you is, we know that standard temperature is 15 degrees Celsius at the surface of the Earth. I want to know what the temperature would be if we climbed to 4,000 feet. And then I want to know what the temperature would be if we then left 4,000 feet and climbed up to 7,000 feet, what the temperature would be. Please put the answers on your paper. Good luck. Have a great day, everybody.